Hello everybody, this is Intikhab Ansari. You can see on the screen the Jamia Millia Islam University in India, New Delhi, from where I got the PhD in 2008. And presently I'm working here in the Jubail Industrial College in Jubail, Saudi Arabia. And my field of interest are superconductivity, okay, high temperature superconductors, especially in the material science. The topic is study of the fundamental and third harmonic AC susceptibility for nano iron doped MgB2 superconductor in presence of the DC field. So this is the topic of for today. The outlines are the fundamental and third harmonic real and imaginary AC susceptibility as a function of temperature or studies here. And we have taken the pure and nano iron doped MgB2 superconductor with different doping levels in presence of the DC applied field with varying frequency. And in the last we have calculated the irreversibility line in third harmonic AC susceptibility, which is shifted towards the higher temperature region when we increase the frequency. And these reports and these are in agreement with the previous report. For the superconductor, there are two important properties. First one is the zero electrical resistance. So when the temperature goes down to zero, near to zero, the resistance drops, and at a certain temperature, it abruptly goes to zero. So this shows the zero electrical resistance at certain temperature, which is called the transition temperature. So superconductor can carry the current without energy loss. And the second property is the perfect diamagnetism. So superconductor can levitate on the above the magnetic field, and this effect is called the Meissner effect. So it's a very common effect on the superconductor when you take the liquid nitrogen and just put the any superconductor into the liquid nitrogen and put the magnet over there, so it will levitate. So this is the Meissner effect. So these are the two basic properties of the superconductors: zero electrical resistance and perfect diamagnetism. The history of the superconductors started since 1900 when the first superconductor came in existence. Mercury has shown the superconductivity, and this it was discovered in 1913 around by the Camernis Owens. You can see here. So, and these are many superconductors up to now, and I'm working on the magnesium diboride MgB2, and it was discovered in 2001. So basically, there are two types of the superconductor. First is the low temperature superconductor, which is has a temperature near to the liquid helium, and the other is called the high temperature superconductors, which have the transition temperature near to 77 K. So these are the basically two types of the superconductor: high temperature superconductor and low temperature superconductor. So there is a Nobel Prize in physics, basically in the superconductivity field. So first was given in 1913 to Camerlin's Owens for the properties of the material at low temperature. And after that, 1972, it was given to the Bardeen, Cooper, and Shiver for the BCS theory of the conventional superconductors. And also in 73, this was given in Josephson and co-workers for the tunneling effect in the superconductor. And 1986, it was given Badnotes and Muller for the discovery of the copper-based superconductor, which is cuprate superconductors. And 91, it was given to Janus for the studies on the complex system, including superconductivity. And in the last 2003, it was given to Ginsburg and Abicosov for the pioneering contribution for the theory of the superconductivity. So this is the history of the in the field of superconductivity. The Nobel Prize was given in 6 times. So why we have chosen the magnesium diboride MgB2? So it has some properties like low critical current density in the high magnetic field, and also the synthesis method is very easy, and it has very low cost material. Magnesium and boron both are low cost material, and it has a strong current flow between the green boundaries. So that's why we have chosen the MgB2 superconductor in this study. So on the other hand, if you see the cuprate-based superconductor, which requires the annoying treatment due to the weak connectivity between the grains in presence of the applied magnetic field. So it is remarkable that real part of the AC susceptibility is related to the flux expulsion from the interior of the sample that directs the superconducting state. And also the imaginary part of the AC susceptibility is associated with the AC losses. So these are some experimental detail. So the polystyrene samples of the nano iron doped MgB2 were synthesized in this method, and we have used the solid state reaction method, and also taken very high purity materials, magnesium, boron, and nano Fe-4. These powders are very high materials, and prepare the sample of the different components, 0%, 1%, 2, 4, and 6 for nano iron doped MgB2. So basically the furnace was kept at 800 degrees centigrade and up to 3 hours in an evacuated quartz tube. So finally we got the polystyrene sample of the nano iron doped MgB2 by this sintering technique. So results in discussion. So we have calculated the two higher order harmonic contributions, which contain the fundamental harmonic and third harmonic basically. And it contains the important information about the Fourier coefficient and require the analysis of the AC susceptibility data in the vicinity of the transition temperature. So the imaginary part gives the single peak at a particular frequency in the temperature region where the coupling phase grows. So we got the peaks at some certain temperature, and this kind of the profile has been explained by the weak link model of the Ishida-Mazaki. And also the amplitude of the peaks in these plots enhances consistently on increasing the frequency from 0.2 to 3 kilohertz. And these all peaks are shifted toward the higher temperature region, as well as when the temperature goes down, and except the 1% nano iron dope sample, the 1% nano iron dope sample is not showing, it's showing the different behavior. So we can see the figure number 1H in the next slides, and it has the highest amplitude of the peak for 4% nano iron doped sample among the undoped and doped sample. If you compare with doped and undoped, the 4% shows the highest amplitude. On the other hand, the 6% nano iron doped sample shows not only the lowest amplitude peaks but also the greatest peak widths among the pure and doped sample, which is shown in the figure number 1J. So figures 2A to J, which will be on the next slide, which explicates the third harmonic real and imaginary AC susceptibility component as a function of temperature for all components from 0% to 6%. We have taken 0 to 6% nano iron doped MgB2 superconductor in presence of AC drive field, which is 0.5 Oersted, and DC field, which have taken around 250 Oersted with varying frequency. The frequency has varied from 0.2 kilohertz to 3 kilohertz. So all the real third harmonic AC susceptibility component articulates the oscillating signals with respect to the zero value. If you see the signals in figure number 2, these are oscillating signals. It is going in maximum value, and other side it has a minimum value. So all these components, third harmonic components in real parts, reveals the sinusoidal nature associated with the ratio, the parameter, delta parameter, which is interlinked to the change of the effective flux diffusivity and connected with the flux spinning interaction. So in the next slide, we will see some graphs. And the first one, this is the first harmonic, which is fundamental in a real part. So when the temperature is going on the lower side, see this is a similar graph. 0.2 frequency is varying from 0.2 kilohertz to 3 kilohertz in the pure MgB2. The first one, A part, is the pure MgB2. So these are all going down, and in 1% the behavior is a little bit different. Here you can see the temperature is transition temperature is near to 34 around, and also in the 2% the behavior is changing, and 4% and 6%. 6% the behavior totally different, and the transition is around to 28 to 32 in between these. So these figures show the temperature dependence of real part of fundamental AC susceptibility. These all figures, which is figure number 1. Now these are imaginary parts of the fundamental AC susceptibility. So here we got the peak at a certain temperature. So first one, this one is the pure MgB2, and 1%. Then it is, if you see in the 2%, the behavior is looking good. We have taken the DC field 250 Oersted and AC 0.5 Oersted. And when you compare the amplitude is shifted toward the higher temperature. We increase the frequency, and the 4% the behavior is a little bit different, and the 6% the behavior is totally different. We have not got to the very sharp peaks, but the wide range. So these are the results, and this is the case in the third harmonic AC susceptibility. In the third harmonic, the signals are in oscillating signals, so in plus direction and also the minus direction. So first one is for the pure MgB2, second one is 1% iron doped. So the graph is changing a little bit. Okay. And in the 2%, it's very clear. In the 4%, the graph is also going up and down, but little bit noises are here. And in the 6%, the behavior is totally different in both the sides. So we got these results in the nano iron doped MgB2 superconductors. And these are the imaginary part of the third harmonic AC susceptibility. So also it had some large peak at certain temperatures in pure MgB2 in 1%, 2%, and also the 6%, the behavior is totally different. So we have taken the DC field up to 250 Austrid and AC field 0.5 Austrid. These are the results of the all harmonics, the first harmonic and third harmonic. So at last, the temperature dependence of the fundamental and third harmonic AC susceptibility components characterized in this and the presence of the 250 Austrid applied DC field and 0.5 Austrid AC drive field with the variation of the frequency. And we also got some peaks amplitude in fundamental harmonic imaginary AC susceptibility, which improves regularly with the increase of the frequency and shifted toward the higher temperature side. So all the peaks are shifting towards the higher temperature range. And we also got the 4% and 6% nano iron dope sample demonstrate the highest and lowest amplitude of the peak among the pure and undoped samples in the imaginary part. And the real third harmonic AC susceptibility component, which exposes the sinusoidal oscillations in the maximum and minimum values around the zero with respect to the zero and related to the parameter proportional to the penetration depth of the AC drive field. And the amplitude of the imaginary component is higher as compared to the real component in third harmonic AC susceptibility plot. If we compare the both component, the imaginary component and real component, this one imaginary component has a higher amplitude in the third harmonic case. And at last, the reversibility line is shifted toward the higher temperatures region when we increase the frequency. So these are some conclusions of these studies. So thank you very much for your attention. Bye bye.